So today we are going to give the theory part of Cauchy's entropy test. So remember we are dealing with infinite series of real numbers. So let's start. So the theory says the following. So I'm going to answer this question: state and prove Cauchy entropy test. So we state the theorem in this way. Let summation un be a series of positive terms such that limit u and this un raise it to 1 by n as n tends to infinity, such that limit un is equal to L, and if L is less than 1, then summation un converges. If L is greater than 1, then summation un diverges. It's very simple. So we are given a series of positive terms, and we are given that the limit L could be less than 1, it converges, greater than 1, it diverges. Okay. So remember, we are not really talking about whether it is finite or not. It's just about whether it is on the right side of 1 or the left side of 1. That's very important. So let's look at the proof. So state and prove is what is generally being asked. So it's given limit un power 1 by n, that is nth root of un, is L. Okay, so we go by limit. We go by definition of limit. This is very important. The starting point is the definition of the limit. So we know that if L is the limit given, look at this, then for all epsilon greater than 0, however small it may be, there exists a natural number m such that this term, whatever term is there for which I'm taking the limit, if I put it in modulus like this, un power 1 by n minus L is less than epsilon for all n greater than m. So what does it mean? It means that accepting first few terms up to m, rest all times, this difference between the un power 1 by n and L is going to be bounded by the small number epsilon, right? So this can be rewritten as L minus epsilon less than un power 1 by n less than L plus epsilon. You could first write it as like this. I have to just write this term, un power 1 by n is what I've written here, less than plus epsilon, and I add L both sides. Adding L in each term, if you add L, you are left with un power 1 by n in the middle and L minus epsilon in the left, L plus epsilon in the right. Okay, of course, for all n greater than m. Yeah, this is what we know. Now we ignore the first m terms, and this is valid. I mean, the theory of sequences says that we can always ignore the first m terms and discuss the remaining terms. Okay, it's immaterial if the first m terms don't behave the way we want. It doesn't matter. So ignoring the first m terms uh, and choose, because it's true for all epsilon. So choose epsilon, and we choose epsilon greater than 0 such that your L minus, no, your L plus epsilon is still less than 1. I want to, because here I'm really concerned about the first condition, L is less than 1. So even if I add epsilon, it should be still less than 1. So so we know that since we know L is less than 1 for case 1. Okay, so this is case 1 I'm looking at. Okay, so now therefore you have un power 1 by n is less than L plus epsilon. And because I'm saying L plus epsilon is less than 1, I can simply say implies un power 1 by n okay, this term which is less than epsilon we may call it as say r, which is a less than 1 term. So un power 1 by n is less than r. So raising both sides to r, by the way, r is a positive number, so it doesn't affect the inequality. So un, I'm having trouble with this pen. Let's, yeah. So un alone is less than or equal to r power n. I'm raising n both sides. Raising both sides to not r n. Okay. So what it means? This means each term in our series un is less than corresponding term. See what I'm doing? Left hand side I've considered as a series. Right hand side also you can consider as series Rn. Well, R is a fixed number L plus epsilon. So this is a fixed number which is less than 1, which is a GP, which is a geometric progression. So we know that GP converges if R is common ratio is less than 1. So therefore, our series summation un is definitely every term is less than corresponding term in the right hand side, that is summation Rn. Therefore, our series is behaving similar to this, so it's convergent. So we are done with the case 1. Case 2, see, we are actually having this kind of an inequality. I guess, yeah. So in case 1, we harnessed this part of the inequality. In case 2, we are going to harness this part of the inequality. So what we will do, let epsilon be chosen such that L minus epsilon. See here, L minus epsilon is less than un power 1 by n, means un power 1 by n is greater than L minus epsilon. So chosen such that un power 1 by n is greater than L minus epsilon, and let us call it as some R. Now, we know for case 2, L itself is greater than 1. Therefore, we choose epsilon such that L minus epsilon is still greater than 1. Okay, we choose epsilon in such a way that L minus, even after subtracting this small epsilon, the status of L being greater than 1 still should be retained even after subtracting minus epsilon. That's what I claim here. Okay, so I carefully choose epsilon now, and you see that for all epsilon this inequality is true. So we have the liberty to choose such epsilon. So what I do, I raise both sides to power n. So un is greater than r power n. So I'm just looking at this is the same is r, right? So I'm replacing L minus epsilon by r because I'm calling it as r, which is a number greater than 1. Therefore, each term in summation un is greater than corresponding term in summation rn. Now you see, compared to the first case, here we have something where the common ratio r is greater than 1. Therefore, since the series on the right, that is a GP with r greater than 1, therefore it diverges. And every term in a left-hand side is greater than such a series. Therefore, our series summation un also diverges. So that ends the proof. Thank you.